Hello all, I welcome you all to the 11th lecture of this course EE 690 ATM. For the last few lectures we have been talking about electrons in periodic lattices, and we went through the free electron situation where electrons were just treated as plane waves of the form e power I k dot r, right? And psi square, the probability of finding the electron, was constant throughout the space. And larger the space, smaller will be the probability to find the electron in that particular in small dk, right? And when we started to talk about electrons in a periodic crystal, we saw that you start to obey some periodicity of the lattice. The electrons were called as block electrons. They were particularly of the form that you take a wave function psi of r, and any of the lattice translation is just e power I k dot r into psi of r, right? So you just add the phase if the wave function is shifted by any lattice constant r. And we found that if the k values are closer to the Brillouin zone edge, then they start to interact with each other, and then you start forming band gaps. And the actual electron solution can be written as this form. So basically the electron solution at any particular k, you have interaction with electrons which are separated by the reciprocal lattice vector g, right? So psi k is written as summation over all lattice constants g. Alpha g is some normalization constant e power I k minus g dot r tells you that you have summation or contributions or interactions between plane waves which are separated by one reciprocal lattice vector g. In the tight binding case, we started to represent electrons not purely by the plane waves but by the atomic orbitals, right? So basically we solved the hydrogen atom, and then we showed that in a Coulombic potential which looks like this, an atom with ion, let's say a positive ion core, the electrons have several energies, and these energies are particularly represented by three quantum numbers n, l and m. And you have increasing energies, particularly like 1s, 2s, 2p, and so on, right? And you can write psi r, which is summation of several atomic orbitals, and the total electron wave function can be written the same way you write the block electron here, right? Summation of blocks translated orbital functions. So these orbital functions, which are summation of atomic orbitals, can be lattice translated and summed. We showed that this is also a block wave function. The main property of the block wave function is this, and we showed that this wave function description also follows that, right? We solved the Schrodinger equation for any particular atomic orbital psi m, and then we came up with this expression whose right hand side we showed is almost always small. This is something which is very important. This is the main consequence of tight binding approximation. It has three terms. First term, which is small because you act the atomic orbital psi m with another atomic orbital of a different atom. If we take a look at this, if we have an atomic orbital here, something like this, and we look at the overlap of this one with a lattice translation, which can be several unit cells away, right? And this is in most cases a very small value, so this always turns to be 0. The same thing is the third term, which is also psi m multiplied by atomic orbitals which are lattice translated, which also comes out to be almost small. And the last and the final one is the overlap of each atomic orbitals with the potential multiplied by this atomic orbital. And this potential u of r is very small. So okay, so to recap, this u of r is perturbation from the isolated atom potential. So the isolated atom Hamiltonian potential is like this, but whenever you bring another atom close to this potential starts to drop right? It turns out to be. So the change in potential, that is which happens here, is only in the interstitial regions here and not in the atomic cores. And these psi m's and psi n's are atomic core orbitals. So under these situations, u of r is a small number. So the entire right hand side is small. If the entire right hand side is small, this can be possible only in few combinations of the left. If b of bm is small, bm is the contribution of the atomic orbital in the electron wave function itself. So basically that is 0. Or the electron energy is very close to the atomic energy em. So that means that only if the electron energies are very close to the atomic energies, you have those orbitals contributing to the wave function psi of r, right? Otherwise they don't contribute. So this was the conclusions from the tight binding approximation. If you have one atom per lattice point, the summation is written like this, which is once again carried over from this expression. Okay, the summation is written like this. If you have two atoms per lattice point, you have to have summation over all lattice vectors r, summation of several atomic orbitals in each atom, and how many atoms that you have in the unit cell. For instance, silicon has 2 atoms per unit cell, right? So that is the FCC with a motif kind of a crystal structure. So the actual wave function should be written as a summation of 3 different summations. So obviously it can be seen that this can get a little bit tedious if you start involving several k values, because for each k you have to have these summations, right? This is one sample calculation from tight binding approximation done for gallium arsenide. So this is just to show that here, let's say this is the valence band. Here you have 3 different lines contributing from 3 different orbitals. So this valence band here is made mostly of p orbitals for gallium arsenide. So what we mean by made mostly of is that, okay, so let me take a step back to explain this diagram. Each of these lines are psi k's, right? Some band psi n's, and these are summation of atomic orbitals psi an by bn. So it was found that for gallium arsenide, this band, particularly the valence band, has contributions only from p-type orbitals, and the conduction band has contributions from s-type orbitals. And when you have p-type orbitals, it typically are degenerate. So you have 3 p orbitals, px, py and pz, and all of these things contributing to these 3 lines. Whereas the s band is non-degenerate. You don't have any degeneracy for s orbitals in an atom. Hence you see all of them falling down to the same value. So you will have one single line representing all of these things. So this is just an example, and this band structure is calculated at different k directions. So this gamma point is called when k is 0, 0, 0. You can see this diagram here. And if you move along the ky direction with x and z to be 0, you get the x, capital X point. That is what you get when you move here. Right? You just change the only one direction in k. The same thing you can do if you move along x direction. You will get another capital X here. You will get another capital X when you move along the z direction, right? So you get 3 capital X's, and you will see this in plus and minus, right? So basically you will have 6 capital X directions. Similarly, you will have 6 capital L. So you will have a L to go along the L direction. You have to take unit steps along x, y and z in each direction, right? So you will get L when you go along that. And when you move from here along y, you change only one of these values, so you can move. So typically band structures are calculated for different k values, for different k contributions, and then they are plotted here, right? Last time when we met, we just had one simple calculation for a 1s orbital. because there is only one s, your summation of atomic orbitals will only have s, right? So bs will turn out to be 1. The wave function is written as summation as these atomic orbitals, and this big equation is what we saw last time. When we reduce it, the total energy of the wave function turns out to be this equation, which seems to be big, but once again we will reduce this, right? So this small term here is an overlap function of the s orbital in one atom with s orbital with several with an atom which is lattice translated. So with this being small, the denominator turns out to be only 1, right? And hence what we will get is ek is es minus beta being some value which is this one minus this expression, which is an overlap of a s orbital with s orbitals in different atoms, right? With the nearby atoms. Obviously this term will give you non-zero values only if this capital R is small. You will not have atomic overlap with atoms which are far away, right? So basically you will have, this is called as an overlap integral. We have just retained this because this will determine how the band structures change. For a simplest FCC lattice where the nearest atoms are in these locations, you can actually calculate this ek expression, which will turn out to be like this. You will get cos kx a by 2, cos ky b by 2, and its summation in the sense it will turn out to be cos ky a by 2, cos kz a by 2, plus so on. And these things can once again be converted into a sine, and sine of a small value will be the same value, right? So you will finally get this as your expression. When gamma is small, you get the atomic energy levels, and when gamma is large, you get the free electron energy dispersion. So this tight bending treatment allows us to get back to different extremes, right? So with these things, we would like to close the chapter on tight binding with few observations. If the overlap is small, then the bandwidth is small, right? So basically what it means is, from here, if these overlap values are small, ek separation from the em will be very small, right? Because if b is non-zero, ek should be very small to very close to em. So this means that the atom energy levels only strongly contribute, so the electron energy levels lie very close to the atomic energy levels. Tight binding is a summation of atomic wave functions. It's also a block, so basically the electron can be found anywhere with a block phase factor. This is something that we know. The group velocity, which will be very important, we will discuss this later on in this lecture. So group velocities is basically, this is the velocity that you can take for a wave packet. We saw this when we are talking about in the quantum mechanics, right? You remember that we talked about the phase velocities and the group velocity, and we saw that if you consider only the phase velocity, it will be twice the classical velocity of a particle. But if you take a particle as a wave packet, then you can actually recover back the classical velocity. So that's why we use only the group velocity, which is like an envelope velocity, which is typically written as dou E by dou K is the velocity of the block wave. It is 0 when there is no overlap. So we go back to this equation. In S, this is a simple 1s case, dou E by dou K will turn out to be 0 if gamma is 0, right? So what we mean is, if there is no overlap, then there is zero phase velocity of the electrons, in the sense that the electrons do not move outside the atom. So when there is no overlap, there is no quantum mechanical tunneling between the sides, the conductivity is lower. Remember that less overlap is also narrow bands. So you will have atomic bands when there is no overlap. When there is no overlap, you also have no conductivity. The sum of the atomic wave functions used in block expansion is called as Vanier functions. It is just for your information kind of a thing. So for what we mean is this summation. The summation that we use, this is called as Vanier functions. Okay. The biggest problem with tight binding is with the problem that these are the summation of atomic orbitals, and you are trying to model electrons which are nearly free, for instance, let's say we are talking about a periodic lattice like this, and the potentials will look something like this, right? Now these are the atomic orbitals. Oops. What I mean is, let's say these are the the wave functions very close to the atom will follow the atomic orbitals. This is fine, right? But the wave function of an atom, of an electron which is far away from the atom, cannot be represented by atomic orbitals, right? It makes no sense. There should be a lot of overlap here. You cannot do the tight binding approximation saying that the overlap is less. So the tight binding approximation, though typically explains very well the behavior in valence band, it does not describe the properties of a conduction band so well, right? So this is the problem with tight binding. So the solution for that is people started to use what is called as the orthogonalized plane wave. So what it means is the wave function of an atom, of an electron very close to the ion, is the atomic orbitals. A wave function of an electron which is free are the plane waves, right? So the solution to this problem that we need to find one method which will cover both the conduction band properties, that is electron wave functions which are plane wave like, and the valence band properties where the electron wave functions are very close to the atomic orbitals, both of them simultaneously, is what is called as the orthogonalized plane wave method. The way to do this is to find a wave function which is being projected like this, such that it also is orthogonal to all the atomic orbitals. Why it is so, we will show soon enough. So now what is typically done is we take a wave function like this, which is a summation of a plane wave with an atomic orbital. So this is the tight binding Vanier functions. You add to the tight binding Vanier functions a plane wave, such that in the places where the atomic orbitals die away, you have the plane waves which take over, and in the places where the atomic orbitals are strong, the plane waves is obviously a small number. So you have a solution which works both in the interstitials as well as in the atom. Now how do we find this psi m? This is given by the solution that it has to be orthogonal to the atomic orbitals. Psi c are atomic orbitals and this is psi k, right? So if we choose such that these functions are orthogonal to the atomic orbitals, how will we do this? We do this particular expansion. Psi an is atomic orbital, so this is an inner product space. If you make this 0, whatever that will remain is just this, right? Because psi an into psi k is just this. So bn's will turn out to be an inner product of psi an with some wave function e power I k dot. And finally, the total electron wave function is written as summation of this psi k's. This is an independent solution, obviously by quantum mechanics. If we find the solution to the Hamiltonian, the linear combination of several such solutions is also a solution, right? So basically this is why we write the electron wave function as a summation of several such functions. So once we have this approach, we once again go through what we did for the tight binding approximation. You take the total Hamiltonian to the summation of the atomic Hamiltonian with some perturbation del u, and if you act the atomic wave function psi m from the left and then you solve, then we can actually find the solution for all the energies. To solve this problem, we need to find the periodic potential and the Fourier expansion of the lattice. We need to find the wave functions of the atoms that are involved, and of course the crystal structure. Once you know all these things, we can actually solve the total Hamiltonian with an orthogonalized plane wave. So the only difference between tight binding is you make a summation of the tight binding wave function with the plane wave. right? So this is what is orthogonalized plane wave method. This is typically used in many places, but the most commonly used method to calculate the band structure is what is called as the pseudo potential method. So what's the meaning? It is just an extension of the orthogonalized plane wave method. So as we saw previously, each of the solution to the Hamiltonian is written like this. This is phi k is phi. So here this is just the plane wave. So I'm just simplifying or writing in short notation the plane wave as phi, and you have a summation of several atomic orbitals. So this is basically tight binding, right? This part is tight binding, and you add to the tight binding the plane wave, and then you get the orthogonalized plane wave solution. If this is the solution, you act with this, the Hamiltonian H, give you H psi. This will give you H psi minus, this is some number, inner product is a number, right? H psi an. On the right hand side, you have E acting on this psi, will give you E psi minus E this, right? And obviously, according to Schrodinger's equation, these two should be the same. So the left hand side is just this coming from here, and the right hand side is just this. So now I move this part to the left, so I get this. Eventually what it will come down to is this equation. You see, these psi's are plane waves. So this is reminiscent of our normal H psi equal to E psi behavior, right? Where H is this summation of this plus some Vp, and Vp is just this. What I'm trying to develop here is, if you use an orthogonalized plane wave method, you can convert the actual potential of the periodic lattice into and convert it into something. You add to something which is called as a pseudo potential, and you write the total Hamiltonian, which is summation of H plus Vp, is this one. So this is your lattice potential, and Vp is our previous definition, right? So it is, you take the energy of the electron and you suppress from the energy the atomic energies, right? So what this approach just basically means is, if you take an orthogonalized plane wave as your solution, then it means that you take the electron energies and you suppress the atomic energies from that. So your actual potential, which was so deep and sharp, now becomes shallow because you have subtracted the lower lying atomic potential. So you get your Vp, which is something like this. And once your Vps are small and you do not have sharp features, then you can clearly see that it will not require a lot of Fourier series expansion. So the number of k values that you take will be small, and the problem will be much easier to solve if you use the pseudo potential method. So it is just an extension of the orthogonalized plane wave method, but then it is just a different way of solving. The method to solve the orthogonalized plane wave method is also called as a variational method, because the way we have approached to this equation, right, it is a variational method. So you get the eigen energies and then see what will be the smallest Ek value to get to overall lower total energy, and that's how this comes down to. So this is called as a variational method, whereas the pseudo potential one is an approximation, and it can be solved numerically. So what we have done is, you use this orthogonalized plane wave functions and you plug it into the Schrodinger's equation. You change the crystal potentials Vr and add to the crystal potential some Vp, which are solutions from the orthogonalized wave function. These are solutions from the atomic orbitals. You bring them here and then you transform the your crystal potential with them, so that you get smaller and smoother features, right? So with these several examples of several methods of calculating the band structures, let's look at few examples. This is an example band structure calculation of silicon. silicon's valence band, as many semiconductor valence bands, typically contain p orbitals. So you have px, py, and pz. So you basically have about 3 bands which contribute mostly to the valence band, right? And the conduction band has several contributions. Several conduction band has s and p, px and py. So basically it has so you have several contributions into the conduction band, giving you the lowest lying conduction band, not at the gamma point but at the x point. You remember we talking about x is you take 0 0 0 and travel along any one of the direction exclusively, you get the x values, and you have 6 equivalent x values. So the smallest gap between the conduction band and the valence band. The valence band is a band in which electrons are fully occupied, right, at 0 Kelvin, and conduction band is the next lying band. The lowest energy level is not at the gamma point but at the x point, right? And you have 6 equivalent Valley points, because you have this x at positive ky and negative ky. Similarly, you have positive kx and negative kx, positive kz and negative kz, right? So basically you have 6 equivalent Valley points, and the gap at the x is about 1.1 eV. This is about 1.1 eV, and this is about 3.4 eV. So basically you have a much larger gap at the gamma point and a smaller one at the x point. This is the band structure of silicon. The band structure of gallium arsenide actually has, as we saw previously, the conduction band is pretty straightforward. It contains only s orbitals, and the valence band of gallium arsenide has p. As we saw previously, it has at least 3 components. So this is one, this is the second, the third one is just not given here. The gap happens at the gamma point because this is an s in the conduction band. It is much simpler. The gap is about 1.42 eV at the gamma. At the L point, the gap is not largely different. It is about 1.71 eV. So because this small separation in the energy makes it to contribute in many ways, you will see differential negative resistance in gallium arsenide. The energy dispersion in the non-parabolic approximation is given like this. You have an indirect band gap at L, which is larger than the direct one. The direct one is about 1.42 eV, and you have 2 valence bands here. Here we are plotting the gallium nitride band structure just for an example. Previously we saw about the FCC structures. This is an HCP structure. The symmetry points are different. Gamma once again being 0 0 0. But then here you have m along each of the direction, and k as you move in a plane. You have kx and ky. You move together in one plane, you get the diagonal one kx. You have a being vertically above, which may not be the same as m, right, because this is an HCP crystal. So people calculate the band structure along these symmetry points, gamma, a, h, k, and again gamma. The band gap here is about 3 eV, which is a wide band gap semiconductor which is used in light emission and high power devices, right? So with this description of bands and its filling, we will finish about this with discussing the static properties of a solid by making few observations. A solid which has 1 electron per unit cell is almost always a metal. Why? Because each of the k, how many unit cells you have gives you unique k values, and each k value can have 2 electrons. So if you have only 1 electron per unit cell, the last band is obviously unfilled, is only partially half filled. So most of the solids with 1 electron per unit cell is almost always a metal. Examples are lithium, sodium, potassium, so on. In fact, solids with odd number of electrons are almost always a metal. There are some there are some exceptions to this, like bismuth and all those things, but then you have 2 atoms per unit cell, so giving you totally an even number of electrons in a unit cell. So basically that does not count. If you have an even number of unit cell, that does not necessarily have to be an insulator, because the bands might now overlap as shown here. So here if you see, there are 2 different directions. The point A as we draw here is along the 100 direction. As you go along the 100 direction, you will meet the Brillouin zone. As you meet the Brillouin zone, the bands kind of taper down, right? This is because of interference, as we saw previously. So your bands will bend like this close to 100 lattice point, 100 Brillouin zone point, right? But if you move along the 110 point, which is given on the left hand side, you can see that you have a lot more points, a lot more distance till you reach the first Brillouin zone, right? So basically this side is much higher than the other side. So when the electrons start to occupy, if the electrons are occupied till here, you can see that the electrons occupy the second Brillouin zone close to the A point, but then they only occupy the first Brillouin zone in the 100 point, right? So basically you will have this disparity in electron occupation. And here if you see that you have the valence band and the conduction band overlapping, right? So because you have occupancy here also, right? So basically you have an overlapping band along the A direction, along the 100 direction, whereas a strong gap in the along the 110 direction. If the topmost band has strong d orbital contributions, we call it a transition metal. You have iron, molybdenum, tungsten, and so on and so forth. A completely filled band at 0K, there exists a gap in the energy following the last occupancy level. So this is called as the band gap, right? Because of symmetry, there can exist no empty state at energies lower than the last filled band. So what we mean is, let's say we have a band like this, and this is the last filled band at 0 Kelvin. You cannot have an energy level which is vacant below the last filled band, right? Because it has to be symmetric. If this is vacant, an electron will fall down, and then you will fill this space, right? So basically it will lower the total energy level. So because of the symmetry considerations, there cannot be any empty state lower than the Fermi surface, so there cannot be any current flow. Electric field, photons and phonons can be used to excite an electron from one energy level to the other. We will see all these things soon. So till the previous point we talked about the static considerations. We did not talk about electrons which were moving, right? So now let's talk about electrons which start to move. We are still talking about nearly free electrons, block electrons, and electrons in periodic lattices. So they are almost always wave functions which are bunched together. So you always form a wave packet. And when we form a wave packet, as we saw previously, we can only talk about the group velocity. The group velocity Vg is d omega by dk, which is written by 1 by h prime dE by dk. This is something that we have seen previously in our quantum mechanical treatment, right? So the effect of the crystal potential is which dictates the velocity. So basically the dispersion, how the energy of an electron changes with changes in k vector is what determines the velocity, right? So if an electric field E is applied, you do some work, you change the electron k vector from k to k plus del k, right? When you have something like this, the change in energy or the work done is dE by dk into del k, and dE by dk is h cross Vg from here, right? So h cross Vg into del k. This is the change in energy due to the applied electric field E. But if we have an electric field E which moves at distance Vg into del t per unit time, the work done is also minus EE Vg del t, right? So this is obvious. If you equate both of them, then we can clearly see that del E is minus EE by h bar del t, And in other words, if we move around, h cross dk by dt, this is h cross k dot is basically f. It can also be so h cross k is also the momentum, right? So classically f is p dot, right? The rate of change of momentum is the force, and quantum mechanically also we have actually derived that h cross k dot is the force that you have applied. If the force is a magnetic field, then h cross k dot is minus e v cross b. So the solution for this equation h k dot is equal to f is k of t is k naught minus, let's say if you have applied an electrostatic force, which will be minus E by h cross into t, right? So basically the k vector, the electron k vector or the wave vector needs to change according to time and the applied field, right? For any change in time and field, the k vectors has to change. But if there exists no other k vector which is free, then the electron can obviously not change, right? So your k of t will remain same as k naught, and hence there will not be any effect of the electric field. Hence a completely filled band will have an infinite resistivity. So what we mean is, let's say the band is like this and it is filled till this point, right? So all the electron levels are filled. So an electron here with k wants to be scattered, but there is no del k nearby to get scattered, right? There is no k which is vacant for it to be scattered. So a completely filled band has infinite resistivity. The velocity, the group velocity, can be also written from this expression at any time t. Is the velocity dependent on the k value? See, the velocity is basically dE by dk. So what we mean is, you take the E versus k plot and look at the changes in k, and that's what will be the velocity, right? If the k moves from here to here, so basically it means that you have much smaller slope than here, so the velocity reduces. If you move the k from here to here, which changes to a different slope with a higher slope, you have a higher velocity, right? So the velocity depends upon the dispersion relation. If the velocity changes so much that the k value gets close to the Brillouin zone, it is even possible to reverse the direction of the velocity, right? So if we keep on changing the so basically here we are plotting the E versus k here, and the derivative of E versus k is the velocity, right? So here you have negative velocities and here you have positive velocities. So if you keep changing, or if you keep applying the electric field such that the velocity keeps changing, it's possible that you reach a point where the velocity starts to change back. So at some point you can also have velocity with changed direction, right? If you reach a k value close to the Brillouin zone, the velocity is actually reverse. So it's possible that even under a constant DC source, you can have alternating current. If the velocities keep alternating between positive and negative values, you will start getting alternating current even under constant DC source. However, this has not been practically observed because you cannot have velocity accelerations like this. More often than not, they get scattered and the velocities gets randomized. Right? So with all these discussions, we have reached the last point of just discussions about holes. We previously talked about bands which are completely filled. We are talking about one such band here. Let's say this is the gamma point, and that is k equal to 0. Because of the symmetry considerations, the band will be symmetric in positive k axis and negative k axis, right? At any point, the total wave vector of all the electrons, the summation of total wave vectors of all the electrons in a band is 0, right? So basically you will have equal number of minus electrons with minus case with electrons with plus case, so the total k vector will be 0. If you remove from this band some electron here or here, right? Let's say if an electron ke is removed from the band, let's call this ke is removed from the band, the total momentum of the electron in this band is minus ke. because it still has an electron with minus Ke, but the electron with positive Ke has been removed, right? The total summation of all the K values in this band will turn out to be minus Ke. The missing electron or hole is said to have a K vector minus Ke, or the total band of the total momentum of the band is minus H cross Ke. Now, to understand this, we are talking about a band which has a maximum at some point. Okay, I'm going to call it K naught. Here I've considered gamma, which is K naught equal to 0, but then it does not matter. I can just consider this as K naught, right? And the energy of an electron very close to this K naught can be expanded by Taylor series expansion, which is E K naught plus dou E by dou K, K minus K naught, plus so on and so forth. This is a maxima, right? When we're talking about an electron close to a maxima, this value is going to be 0, and dou square by dou E is going to be a negative value, right? So Ek is written like this. The velocity is 1 by h cross dou E by dou K will turn out to be minus h by m, K minus K naught. Finally, the acceleration will turn out to be minus h k dot by m, right? This is k dot. Acceleration is d by dt. So if I differentiate it one more time, I get minus h cross k dot by m. So what it means is k dot, so basically k dot is force, right? So basically we have minus force by m. So the second derivative is taken to be negative of the band maximum. So the acceleration is found to be negative of the change in momentum. So k dot is the change in momentum, right? So the acceleration is negative of change in momentum. That means that the particle moves as if the mass is negative, right? So basically F is minus ma, and this is possible only if the mass is negative, or in the event of the applied electric field, force being electric field, the particle moves as if the charge is positive, right? So for an electron very close to a band maximum, the electrons move as if the mass of the electron is negative, or if the force is an electrostatic force, it moves as if the charge is positive. The exact opposite will be observed if the particle is near the band minima, right? Why? Because instead of a negative here, which comes from the dou square by dou K square of Ek, right? Because the second derivative close to a maxima is negative, whereas the second derivative close to a minima is positive, right? So if we get a positive value, then this value will become positive, and all these things will still make sense, right? So basically an electron will behave like a normal classical particle with positive mass when it is close to a band minima. When the electron is close to a band maxima, it will behave as if it has a positive charge or a mass which is negative, right? So we will close these discussions with one small discussion regarding the effective mass. The acceleration, as we described here, is v dot is dou by dou t 1 by h cross dou E by dou K, right? This is the velocity, and 1 by h cross can be taken out, and dou E by dou K can be written as 1 by h cross dou E by dou K into dou K by dou T, right? So this dou K by dou T can be replaced, and this will be finally written as 1 by h bar square dou square E by dou K square E, and E is obviously the force, and this is the velocity, right? And if we compare this with the Newton's equation, this equation or this term turns out to be inverse of mass, or called as reciprocal mass. So this is written as, this is called as a mass tensor, and particularly true when we are talking about electrons which are wave packets, right? Because only for a wave packet the velocity is given by this expression, right? If for a wave packet the mass is basically a tensor, if the energy surfaces are written like this, as is a parabola with different dispersions in different directions, then you will have what is called as a tensor. The effect of accelerating an electron in different directions will now be different because it experiences different masses. right? So with this discussion we will stop now, and we will meet for the discussion time. Thank you.